morning everybody. In this fourth class of this D block and F block elements, we will be talking today starting from the different oxidation states of the D block elements. Okay. So, we will be talking about the stability, the corresponding stability of the 3D, 4D and 5D elements. And while talking about their corresponding positions, now we very much know that where the D elements are in the periodic table. So, their positioning in the periodic table also let us know something related to their group number. So, their group we know, and how this particular group number can take us to the corresponding limit of the different oxidation states, because as we have defined these elements having some unpaired electrons in the D level, whether it is a 3D or a 4D or a 5D level. So, these number of electrons in the D level basically, whether we can knock out them nicely to get a particular oxidation states from metal in the elemental state. In the gaseous state, sometimes we will find that these will also give us some loss of electron. So, loss of electron will take us to a corresponding oxidation state, whether it is a bivalent, trivalent, etc. But how many of these electrons we can remove from a M0 state? That means, whether this particular group number can have some role, and what is that particular role which can be functioning very well with 3D elements or 4D elements or the 5D elements. So, we will define something which we will consider as group oxidation state. So, group will tag this particular oxidation state. So, this basically tells us that it can be achieved by elements that lie towards the left of the D block. So, if we consider that occupying these D levels from D1 to D9, we are having some elements, and on the left hand side, say below D5 system, we are having some elements, and on the right hand side after D5 electronic configuration, we can have some other elements. So, towards the left, that means towards D1, D2, D3, D4 and D5. So, this can be achieved by the elements very nicely, and oxygen is usually more effective than fluorine at bringing the highest oxidation state, because of less crowding is involved. What does it mean? That means, if we want to go for a corresponding group oxidation state, and we will be considering something where we basically go for the stabilization of the species by O2 minus or F minus. So, the highest possible oxides or highest possible fluoride, whether we will get that will basically tell us that whether we will be able to achieve that corresponding group oxidation states for that particular element. So, the oxidation state, that means, if we consider it is manganese. So, manganese 0 to if we go for manganese 7, that means heptavalent manganese state. So, we have to remove minus 7 electron to achieve that. And oxygen or any other electronegative element, oxygen or fluorine, can take up those electrons to go from elemental oxygen or gaseous oxygen to O2 minus, that is the oxide ion, or fluorine can also go from fluorine itself to fluoride ion. So, these are very small groups, and the required number of those species. That means, for this, if we write something which is Mn2O7, where this manganese is present in the heptavalent state, and this heptavalent state can be achieved in presence of these oxides. So, this is the oxide compound of manganese, where manganese is present in the plus 7 oxidation state. Similarly, fluoride. So, these are very small groups and many number of these small groups can be surrounded by this particular metal center. So, what we get, we can achieve with these oxide and fluoride environment the highest possible oxidation state or the group oxidation state. And these are basically related to the ionization energies what we are discussing so far. So, these ionization energies, so the amount of energy we just require to remove those electrons from this D0 to corresponding manganese in the 0 oxidation state to manganese in the +7 oxidation state. So, successive ionization energies, so one after another. So, the first electron removal, the second electron removal, the third electron removal and so on. So, the successive removal of these electrons will give you ionization energy for the first one, ionization energy for the second one, and the successive ionization energies basically rise, because if we move from manganese 0 to manganese 1 plus, then to manganese 2 plus, then to manganese 3 plus, what we will see that we will having the ionization energy or ionization enthalpy for the first one, the first electron transfer, IE2 is for the second, IE3 for the third electron transfer, but the magnitude of these ionization energy or IE values will rise sharply compared to the other values. So, if we just compare with this manganese or the technetium or the rhenium along the group where it is the 3D, it is the 4D and it is the 5D element. So, in these particular cases, if we try to compare the ionization energies, so ionization energies for the corresponding technetium or rhenium for the monovalent, bivalent, trivalent and so on would be less compared to the manganese state. So, that basically tells us other thing also, that if we just can reach up to an oxidation state of complete removal of all the electrons, that means manganese 7 plus where no electron is there. Similarly, for technetium and for rhenium, which is also rhenium 7 plus. But depending upon these ionization enthalpy values, this particular species, if we try to compare that this particular species in the heptavalent state compared to the rhenium in the hexavalent state, this is less stable. So, in terms of simple stability, we can consider that stability means that it will not easily go to this particular heptavalent oxidation state. That means, it will try to reduce very smoothly or very effectively or very much readily as and when electrons are available to this particular system. That means, if we get this as a less stable species, at the same time it can also be considered as the more strongly oxidizing species. So, it will be strongly oxidizing as well at the same time compared to rhenium 7 plus. So, since this is the number, so we are talking about this particular 7 oxidation state. So, for group 7, which is our the corresponding group oxidation state, that means whether we will be able to remove all the 7 electrons from the nuclear attraction of the manganese nucleus, we will be getting manganese from here to manganese 7 plus, and if the corresponding oxide ions are available. So, those oxide ions are basically giving us some idea that this can be there, since we have already told you that this oxide ion will be readily available for stabilizing the higher oxidation states. So, MnO, this particular species will be available there. So, to go up to this particular species, this is a dimeric compound of Mn2O7 species, but if we stick our attention, if we concentrate our attention on the species which would be mononuclear and in the solid state or in solution, we will find that 4 of them that means manganese bound to 4 oxygen as oxide ions like this can be a stable entity, and this manganese is in +7 oxidation state. So, we will have 1 minus charge over this species. So, which is nothing but the well known permanganate ion or manganate 7 ion. So, oxide ions will be available to stabilize this manganese, which has a group oxidation state of 7 and which is by definition will be strongly oxidizing. So, if we try to compare this particular oxidizing power, and as we go down from manganese to rhenium via technetium, we can have the analogous species. So, analogous species will be pertechnate ion TCO4 minus and perrhenate ion. So, these two species, what we get here, if we try to compare now the oxidizing ability of MnO4 minus, TCO4 minus and ReO4 minus, and as we know that from here from manganese to rhenium, these are more and more stable, that means they are less oxidizing. So, only this MnO4 minus, that means permanganate anion, will be strongly oxidizing compared to TCO4 minus or ReO4 minus. So, this will be higher than that of your TCO4 minus, and this will be higher than that of our ReO4 minus in terms of your corresponding oxidizing ability. So, MnO4 minus will be the strongest one in terms of the corresponding redox potential values. We can also consider these things. So, ionization enthalpy value, which is responsible for the more and more electron transfer from the species in the gaseous state as well as in the solution, and these mostly in solution we can compare the corresponding electrode potential for the corresponding oxidizing ability of the permanganate ion compared to that of our perrhenate ion. So, what about the next one, that means the group 8. So, if we just go for the group 8 elements. So, group 8 element, we know that it starts from iron having one more electron, that means you can we are able to remove 8 electrons instead of 7 as we have seen for manganese. So, the next one is ruthenium and the third one is osmium. So, it's possible to remove all the 8 electrons from there. As a result, what we get, that means iron can be obtained in +8 oxidation state. So, that basically gives us some interesting idea that whether the existence of this is there as FeO4. But as we have defined in the previous case, in case of manganese, that these are not so stable, MnO4 minus was not so stable and it will try to reduce itself very quickly to go down to lower oxidation state. So, this FeO4, if it is at all exists, so it will be highly oxidizing and very quickly can go for its reduction, and as a result this is not known. So, it is a unknown species, it is an unknown species which we cannot get. But for the other two, that means if we just the corresponding one will be RuO4 and OSO4, and as we go down the stability is increasing from iron to ruthenium to osmium. As a result, we can have some chance that RuO4, ruthenium tetroxide and osmium tetroxide had come some stability, and experimentally or the actual fact what we can have is these two, that means RuO4 and OSO4 are little bit stable compounds, though they are still oxidizing, but they are stable compounds. So, these basically can give rise to some example that group 8, that means the group oxidation state what we are discussing now, can be achieved for the elements which are in the lower part, that means the 4d and 5d elements having bigger d orbitals. So, if we go for achieving the corresponding noble gas electronic configuration for group oxidation state, so in case of manganese we find that we can go up to manganese 7. Similarly, for ruthenium and osmium, for 4d and 5d elements we can go for ruthenium also in +8 oxidation state and osmium also in +8 oxidation state. Okay. So, this group oxidation state thus tells us that we can have it. So, this one can be there. So, U is never attained after group 8. So, once we reach group 8 for ruthenium to osmium and which have some meaningful existence of the corresponding tetroxides, this basically limits the maximum oxidation state. So, beyond this we cannot expect that we can remove 9 or 10 electrons from the sphere with an increase in ionization energy. So, this is the limit. This is basically limiting our corresponding achievement for the group oxidation state. So, maximum oxidation state what we can reach there is +8 for this group, and noble gas character from left to right across each series of the D block can change. And if we go beyond, that means this particular one already we have excluded, that iron we have excluded, since we consider these for 3D series of elements. That means the group starting from 8 to 12, that means iron, cobalt, nickel, copper and zinc. So, in all these cases we cannot remove all the electrons in this way. So, they again go down to a lower oxidation states. They can give rise to only the bivalent or trivalent or only the bivalent species. That is why we all know that iron can be present there as iron 2 plus or 3 plus, or in some extreme condition we can go iron to up to 4 in solution state, but we cannot get very easily to +5 or +6 oxidation states. So, from the left basically we cannot have we have the limit for these groups. So, the earliest metals basically from scandium to titanium, so they can have these groups. So, instead of stabilizing the very difficult fluoride ions, you can get that these are available for the corresponding chloride. So, group oxidation state can be achieved by simply scandium trichloride SCCl3 and for titanium tetrachloride, that means TiCl4, and these are very useful compound, have some catalytic effect also. But thing is that you can have the chloride environment for these, and this particular thing can stabilize this particular chloride environment and the corresponding highest possible oxidation state. So, the most oxidizing halogens, basically the fluorides, can achieve the other groups. That means, if we just go from scandium, titanium, then vanadium to chromium. So, this vanadium to chromium, which can also form VF5 or CrF6, that means the pentavalent vanadium, then vanadium fluoride in +5 and chromium hexafluoride. So, this pentafluoride and hexafluoride can give rise to the corresponding group oxidation state. So, we see that the group oxidation state can be achieved by these compounds as the fluoride compounds, and which is stable in the solid state also. As we move chromium, so this is the corresponding one for iron what we are just discussing. But as we passed the group 6, the fluoride is a very small one, even fluorine cannot produce the group oxidation state. So, in these cases, in these two cases, that means the group 7 and group 8, we do not get any corresponding existence of manganese heptafluoride and iron octafluoride. So, these basically, as we have just seen, that can be stabilized little bit with the oxides, but cannot be stabilized by fluorides. So, this is the corresponding situation where we can have all these differences. So, another interesting example what we can get this can be a very good example for a typical analytical procedure or the laboratory examination of some species or the test where we are starting from potassium dichromate. So, at the end of this class or in the next class, we will be discussing how we can prepare the corresponding sodium dichromate or the potassium dichromate. This we have already discussed that these are very good oxidizing agent for the redox titrations while we are discussing the redox reactions. So, any reducing agent or any reductant can be analyzed quantitatively by doing the corresponding redox titration using the solution of potassium dichromate. So, this one example is also some test. So, this is basically an analytical test also or a qualitative detection which can further be utilized for some other quantitative reactions. So, what we are getting? We are getting something where we basically see that this particular case, that means the chromium which is present in the left hand side in the potassium dichromate is in the chromium +6 oxidation state, and we are talking about the stabilization of these two things, that means the higher possible oxidation states or the highest oxidation states for the group. So, highest oxidation states for that particular group. So, as we go to the group 6, so chromium we know that it can be stabilized as the hexavalent chromium, and the typical example what we have taken is for the chromate and for the dichromate. And just now we have seen that it can be stabilized by the corresponding oxide ion, or it can be stabilized by fluoride ion, or it can be stabilized by chloride ion. So, these stabilizations what we see is that these hard anions, so this can stabilize the higher oxidation states very easily, and if we put all of them as oxides, so we get in the hexavalent state is the chromium trioxide. As we know, for the corresponding non-metal condition in this group is that corresponding that of your sulfur. So, sulfur we also know sulfur can go to the hexavalent state as sulfur trioxide. So, these two are basically acidic, they can react with water to give rise to acids. So, this is the cases, these are the cases basically for the corresponding stabilization in the hexavalent state. So, now if we take whether the same species these two, because if we say compared to these the corresponding stabilization of chromium with fully fluoride or chloride, that means CrCl6 2 minus, it has also some stability, but it is not so stable, then we can go for the combination, that means the mixed ligand environment. So, the mixed ligand environment if we consider, which is the corresponding mixed ligand environment for the same chromium 6 plus. So, what we can get whether some species like this, that means for the sulfur we know that one particular species is SO2, Cl2 is known. Similarly, if for chromium whether we can get that as a neutral species which is still hexavalent for chromium, which is CrO2 Cl2. And the test, if we can have a laboratory test, the test can be utilized for the detection of chromium, any unknown sample, whether we can have K2 CrO4, any unknown sample we can analyze, or it can be K2 Cr2 O7, the potassium dichromate. As the species what is forming typically is the identifiable one, and which is stabilized in presence of oxygen as well as chloride. So, this can also be a test for any chloride salt like sodium chloride or potassium chloride. So, we all know that how the sodium part or the potassium part can be identified by doing for the corresponding the flame test. So, this sodium and the potassium part can be identified by simply seeing the characteristic color of the sodium and the potassium within the flame. When they are present, because the same salt we are analyzing for the flame test, so the same salt, sodium chloride and potassium chloride, can be nicely utilized for the chloride functioning or the chloride estimation. So, we have taken the example of this particular reaction where potassium dichromate is reacting with sodium chloride and in presence of sulfuric acid, giving rise to a species what we are just looking for, whether we will be able to get that particular species of CrO2Cl2 and the production of potassium bisulfate, sodium bisulfate, all these, because we are handling both sodium as well as potassium ions in the medium, and we are trying to identify this as from sodium chloride, not from potassium chloride. If it is potassium chloride, we will be getting only all KHSO4 with the elimination of some water vapor. So, this is basically well known some test for chloride which is known as the chromyl chloride test. So, is the chromyl chloride test where the chromyl group is forming, that means is a red liquid which is forming over there due to this particular reaction. That means presence of these two, that means these two, the dichromate and the sodium chloride will forming this, and in presence of sulfuric acid, because sulfuric acid is required for this corresponding maintenance of this thing as the removal of the sulfate of the sodium and the potassium ions in this. So, this basically again a particular species which is stabilized in hexavalent state, but the species is CrO2 2 plus, and the name of this species when it is a chloride salt we are calling as the chromyl. So, CHROMYL. So, we can have a species, that means in the ionic form we get a species which is quite stable and which is the chromyl ion. So, as we move for the hexavalent state, we see that since we are talking something, because in the solution we can get the chromium as plus 3, but as it is oxidized we move to a chromium hexavalent state. We already discussed this in previous classes, that the presence of oxide ion to the center can stabilize this in the higher oxidation state like that of vanadil, the molybdenum, the uranyl. So, this is the chromyl, basically in the same way the chromyl ion is forming, and chromium also can in some complex compounds we will be seeing afterwards, that if it is there only one oxo species, that means the chromium in the hexavalent state and this species is in oxygen. So, is 4 plus. So, one oxygen present with chromium is also another separate entity. So, this particular one, so chromium, so this particular species when it is present over there like that of our chromate ion is again a tetrahedral species. So, that tetrahedral species like SO2Cl2 can have some existence and which is a red liquid. So, this red liquid can be formed in a reaction medium. So, what you see here instead of a test tube, because it is a stoppered bottle, because it is a vapor. So, vapor is also forming. So, vapor is also is not so good for our health reason. So, if we can have, if we can make it, you can stopper it and we get that as the red liquid with some brown vapor. So, this is the typical thing what we call as a chromyl chloride test, which is a very characteristic one for seeing that thing that it can be stabilized. The chromium in the higher oxidation state can be stabilized in presence of both oxygen as well as chlorine as chloride ion. So, it is basically heating of the suspected species containing sample suspected of containing chloride. So, any chloride salt can be analyzed with this particular species. So, any chloride salt. Okay. So, chloride salt can be very nicely identified, forget about the other test or other wet test for chloride by silver ion. We all know the silver ion can be used for the identification of the silver as silver chloride is a white precipitate. So, this basically red fumes, and when we stopper it we get a corresponding red liquid. is evident, and the color is a very characteristic one. So, since we are adding dichromate as the chromate source, so the chloride salt, this will only be formed when you have the chloride in the unknown sample, because the corresponding iodide or the fluorides or the bromides are not known to have some stability in this regard or at that much stability for this part. So, if we go for a typical trend of the higher oxidation state, as empirically what we have seen, that the oxides and the fluorides can stabilize these particular oxidation states. So, there will be some trend, and definitely what we see that all the oxides and these particular oxides from these, that means from left to right, that means group 6 to group 7 to group 8. As we are talking about the going from the down, that means from iron, ruthenium, osmium or the chromium, molybdenum and tungsten, these we have already compared. So, any other series, the group 10 in a particular group, whether it is group 6 for chromium, group 7 for manganese or group 8 for iron, there is the typical trend for this, and which is basically decreasing. So, that is why the lower species, that means the corresponding perrhenate or the corresponding osmate as the osmate also in the corresponding hexavalent state, we get that these are the species. So, in a particular oxidation state, now we are trying to compare these oxidation state, all of them are hexavalent. So, chromium is in hexavalent state, manganese is in the heptavalent state, and this is again hexavalent state. So, they are strong oxidizing agent and they are becoming stronger, even the oxidation states are also different. So, this is basically we go for this, if all of them are not for, this is permanganate, this is not, it can be 2 minus also the manganate, MnO4 2 minus. So, MnO4 2 minus, CrO4 2 minus and FeO4 2 minus. So, as we move from left to right, this has some stability already, we know we can handle in the solution for the different taste for that corresponding titrimetric method, the redox titrations and the chromyl chloride test also, but we cannot handle this one which is highly oxidizing. So, as we move from left to right for the different group number from titanium to zinc, and as we go for the different halides, this is again a table which is there in your CBSE book. So, if we just nicely follow that particular trend, what we can get for this your book, that what are the species what we can get basically for these common oxidation states, which is bivalent, trivalent and in some cases are tetravalent. So, what we see that in most cases, that means for the lower end, that means for the titanium and the vanadium, all of them are labeled as X, that means X is ranging from fluoride to bromide. So, this fluoride, chloride, bromide and iodide, so all will be there, and this can be stabilized nicely with all these except this for titanium. So, titanium in the lower oxidation state, which can have some different stabilization which we cannot get for all of them. So, these are basically this X is the fluoride to iodide. So, when only X is present, so all of them are stable, that means in the trivalent and tetravalent state for the titanium, it can be stabilized for fluoride to iodides, but for the bivalent state it is only that particular groups can be stabilized from chloride to iodide. So, we cannot go for the lower oxidation state with that of our fluoride. Similarly, for manganese also the tetravalent and trivalent is only stabilized by fluoride salt, only the bivalent we can have the other salts. So, that is why the laboratory, in the laboratory also we basically handle the different salts. So, manganese X2, that is manganese can be manganese fluoride, manganese can be chloride, manganese can be bromide, and in some cases though the stability cannot be so high for this particular species, because when the iodides are bigger, we do not get much stability in the solid state also for the manganese iodide. Similarly, for these, similarly for the cobalt also, and this is also a very good example for the cobalt fluoride as the cobalt COF3. So, like that of our iron or manganese, so cobalt F3 is forming for in the trivalent only. So, the small anion which is available for stabilizing this particular cobalt center only in the trivalent state. So, what we get basically that the cobalt is present in the +3 oxidation state, and as we just see consider that we can have fluoride ions in our hand, and these two can give rise to the corresponding cobalt F3 species. That means, it can stabilize this particular ion. But this afterwards also, when we will study the coordination chemistry or the coordination compounds, we will see these can also function as very good ligands. So, more and more ligands we can accommodate there. So, this is a discrete solid sample. So, this is a typical salt, cobalt fluoride, the trivalent or the cobaltic fluoride is the salt. But if these ligands are there, so more number of ligands we can accommodate around this cobalt center, and this is a very good example. Afterwards, we will also talk about the corresponding properties of these complex. So, this is the corresponding COF6. So, hexafluoro cobalt 3 ion. So, this hexafluoro cobalt 3 ions have some existing, since this is has the corresponding stabilization, but we may not get it for the corresponding chloride, bromide or iodide species, those are bigger. So, small an ion which can function differently for these ligands, and the property of these ligands compared to the other halides like chloride, bromide and iodide would be completely different. That is why this has some existence, and it has some property related to the corresponding magnetic moments and all these things that we will discuss afterwards. So, going back to the table, that means the cobalt fluoride. So, it is stabilizing in this particular form. Nickel is also only in the bivalent state, they are stabilized for all the halides. Then similarly, the copper, this means the copper in the cupric state, basically it is ranging for this X2, that means for fluoride and chloride only. So, copper will be stabilized in copper 2 fluoride and copper 2 chloride. So, that also give rise to some example that why copper 2 iodide or copper 2 bromide is not much stable, because copper 2 center in terms of this electron transfer behavior or the E0 value is oxidizing, and these bigger halides are also oxidizing. So, copper 2 itself basically will oxidize the fluorides like bromide or iodide. Basically, we will know that this particular reaction can be the basis for the iodometric reaction when copper 2 is reacting with iodide, giving rise to the corresponding liberation of iodine, and that iodine can be titrated by sodium thiosulfate. So, this is there. So, the stabilization is for these two, that means the fluoride, then the smaller in the series, the smaller fluoride and the smaller chloride. Similarly, for the cuprous copper, it is for the copper, this X is 3. So, that means it is for chloride, bromide and iodide. So, if we go for the bigger halides, once it is reduced, it is a very interesting thing that once you reduce this copper center by all these halides, that means it is liberating the corresponding iodide or the corresponding that iodine or from the iodide salt or corresponding bromine from the bromide salt. What we can get that this particular one is only giving us the corresponding copper as the cuprous ion, and this is when stabilizing, that means if the iodine is liberated, then means some amount of iodide is still available in the solution, and that available of that particular iodide will basically attack or take out this particular cuprous ion, and that cuprous ion can be removed as the corresponding cuprous iodide. So, starting from these, similarly for the chlorine, though it is not available for the corresponding liberation of the chlorine by using copper, but it can have some stability, that means in the solid state or in some solution in some non-aqueous medium, you can have some CuCl, that means cuprous chloride as well as the cuprous iodide or cuprous bromide. Similarly, zinc, but for the zinc it since again is of different type, not of the transition element type. So, it can have some stabilization for all the 4 halide groups. So, this basically what we have already seen, that highest group oxidation state can be achieved if we move from the corresponding scandium. So, scandium immediately we can write that the scandium in the highest possible oxidation state is scandium +3. Similarly, for manganese it is also +7. So, the two species what we can get in the oxide environment is the Sc2O3, similarly for manganese it is Mn2O7 that we have already discussed. And these also we have discussed earlier. So, these are also examples in your textbook, in your CBSE book it is there nicely, but as we have seen that how we can stabilize these as the vanadium, as the vanadium 5. So, scandium, titanium, then vanadium, all 5 electrons can be removed. So, this particular the dioxo species, so vanadium dioxo species is there. If it is a vanadium that is corresponding of 4 basically, so this is basically VO plus. So, this is basically VO2 plus and VO2 plus, and all these species are differently forming with the oxo 1. So, this like that of our fluorides. So, like that of our fluorides, basically we get that manganese, we have seen that we are going from here to up to this. So, manganese will have as the different oxide, it has the typical existence of the highest number of oxides at the middle. So, the stabilities of these groups, particularly the highest possible oxidation state is in the. So, basically if we just look at the map of these compounds on the left hand side, these are much more and they have something which is towards the higher oxidation state. But as we cross this particular group, we are just going with the on the right hand side. So, again we are just going down. So, these are not have much stabilization for this particular species, and they are also some typical oxides. So, this is the highest possible or the highest possible existence for this, but for the group 8 we have seen that it would be ruthenium tetroxide and osmium tetroxide, not the corresponding one as this one. So, this is again a very typical compound, and manganese is in the highest possible oxidation state. That means manganese size as charge is very high, and the corresponding size is also less, and from the Fajan's rule we know that the covalence is also increasing. So, is not any the corresponding compound is a typically covalent compound and is not a solid one, is not a solid oxide, is only a green oil. So, this particular one will be highly oxidizing and will therefore be also highly reactive. So, quantitatively if we now compare the corresponding M2 plus to M standard electrode potential and what are the observations we can get. So, that is very important to know again from your book, the table. So, the removal of electrons. So, basically that for the atomization process and the ionization process and the electron removal process and the hydration energy. So, these are all energy contribution, and when we reach the typical E0 value. So, these are the different thermochemical data in kilojoule per mole for all these steps. So, we can have 1, 2, 3, 4 steps to reach this E0 value for the 3D elements from titanium to copper, and we get the corresponding standard electrode potential for the reduction for the bivalent state. That means, the nickel 2 plus 2, nickel 0 is minus 0.25 volt. Similarly, copper 2 plus to copper 0 is also 0.34 volt. So, ultimately the values what we get, and we get a typical trend, and that trend will tell us that how quickly we can go for this reduction. And we all know that there are metal ions, metal atoms also, or the metal rods are also, which can nicely liberate hydrogen from the acids. So, how good they are for the reduction of H plus. So, this reduction of H plus is also a corresponding chemical challenge for the system like that when we just liberate hydrogen. So, hydrogen is liberated and is also a biochemical challenge in the biological system also, because we know that this particular one, when it is removing hydrogen, we know that the different hydrogenases are there. So, bacterial origin or the biological origin is also sufficient to reduce this. That means, the electron can be transferred at a suitable potential, and we know that the hydrogen electrode potential has the standard potential as 0.0 volt we consider. So, removal of these. So, how good those metal atoms or the metal rods or the metal sheets in removing this hydrogen from these corresponding acids, and what we have seen that if the metal is added, and we know that the corresponding metal is giving rise to the corresponding salt, M will be going to M2 plus. If we are reducing the corresponding hydrochloric acid, we will be getting the corresponding metal chloride as the salt. That sulfuric acid will giving rise to sulphate salt, nitric acid will be giving rise to the nitrate salts. So, what we see here is that the different trend basically. So, ultimately this particular column is important, that means the E0 values are important. So, minus 1.63 volt we go to minus 0.7 C, because the zinc is also a very important species. And in electrochemical term, in terms of the electrochemistry, we know that the zinc has a typical electrode, and the copper is also a typical electrode, because these last two things we just basically study from our earlier classes, in earlier science classes or the chemistry classes. We study the corresponding potential for zinc and copper, because these are the corresponding half cell electrode potential, whether your copper center is going from copper 0 to copper 2 plus, or zinc is reducing from zinc 2 plus to zinc. So, if we combine two half cells, so this is for one half cell and zinc is for the other half cell, we get for some E0 value, and whether the reaction is thermodynamically favorable or not, that we can understand. But very small and very simple reactions we can think of. So, what should be the behavior in terms of the corresponding E0 value? What we have seen just now, that the corresponding E0 value copper is 0.34 volt. So, which is important to understand the corresponding behavior of copper as the copper rod or copper metal, or copper as the copper 2 plus in its ionic form. So, since it has a positive potential of 0.34 volt, so it has a positive value, accounts for its inability to liberate H2 from acid. So, copper cannot be available for removing that particular hydrogen gas from the corresponding acids, that means it cannot reduce H plus to give you H2. So, this is therefore that is the copper based anything. So, copper based electrode, copper based electrochemical thing, or copper based corresponding metal enzymes which are there in the biological system may not be very unique for the going rise to the corresponding hydrogenase reactions. But we know from our earlier school days that we know some reaction of copper with acid. What is that acid? That acid is our nitric acid, and sometimes is simply hot and concentrated one, and also for the sulfuric acid, which should be hot and concentrated. So, in these cases only the nitric acid itself, which we all know that is a typical oxidizing agent, and sulfuric acid is hot and concentrated condition, can react, and these acids can be reduced when acids are reduced. So, this is wrong, this is all acids are reduced only. So, we can have a general trend towards less negative E0 values across the series is related to the general increase in the sum of the first and the second ionization enthalpies, the IE values. So, IE values are always important, because we do not know the trend basically whether your IE1 is more than the IE2, and when we sum up these two, we basically get the overall IE values for electron transfer from the M0 state. And there will be a difficult thing where we can understand the corresponding half filled cell or the full filled cell, that means the manganese in the plus 2 state. So, when the D sub cell is reaching manganese 2 plus or to zinc 2 plus, they have some extra stability. So, the stability of the half filled and the full filled cell will tell us something, and tell us some stabilization corresponding to the E0 values and the thermodynamic driving force to achieve that. So, this basically we get for the some other elements for this particular potential. So, as we see that these are now in the horizontal form, it is also again there in your book, but you should nicely follow this trend basically when we move from left to right, and the copper is only having the positive potential value, that is why it is not reacting with acid to liberate hydrogen. But what about this potential? Because these potential are also very interesting to note and interesting to understand when we go for a corresponding bivalent state to the trivalent state, as we know for the iron. So, this iron potential is always very important, and always we should remember wherever we go that whether we can oxidize some ferrous state to the ferric state even for the redox titrations. So, we all know that the permanganate ion or the dichromate ion, they are highly oxidizing. So, these potential values, these E0 values for the corresponding reaction where the dichromate, that means the dichromate ion is reducing back to the chromium 3 plus, or the permanganate ion from the manganese 7 plus to manganese 2 plus is going, what we see that whether those potentials are sufficient to oxidize iron from plus 2 to plus 3. Similarly, we can also consider that the other oxidizing thing, that means on the two sides, the adjacent sides, because the iron we can oxidize. So, this particular iron is for the liberation of hydrogen from the elemental state when iron is going from iron 0 to iron 2 plus, and in this particular case it is for the redox titration. So, all these potential values are important. So, little bit we can have some idea about these potential values and their driving force, but if we move towards the left of this iron, the ferric ion, from left to on the right, that means the manganese in the +3 and cobalt in the +3 oxidation state. So, that is very interesting. So, unlike iron, so iron is not so oxidizing. So, iron 3 plus has some stability, but manganese, that the trivalent manganese and the trivalent cobalt are not so stable in the reaction medium, and that basically gives us some idea that they are the strongest oxidizing agents. So, chromium in the trivalent state and manganese in the trivalent state. So, any salt or any complex ion, what we will see afterwards, that trivalent manganese, that means the manganese trichloride or chromium cobalt trichloride will be some oxidizing agents. Even some organic transformations also we can use them as very good oxidizing agent, but as we move towards the left, these are all negative. So, basically these potentials are all negative. So, this in the +2 states will have some stabilization for in the +2 states. So, they are the strong reducing agents. So, that is why chromium, vanadium and titanium, all three ions in aqueous solutions can serve as a very good reducing agent. These two can serve as oxidizing agents, since the potential is telling us these potentials are high and then the positive side, but these are negative and towards the left. So, they liberate hydrogen from the dilute acids. And the highest value for all these cases in the here is for the zinc, the highest value for zinc is due to the removal of the electron from the stable D10 configuration of zinc 2. So, it is not given here, but the zinc from this particular bivalent to trivalent couple has a very high potential value, because we cannot go to zinc in the trivalent state. And the comparatively low value for the vanadium, we see that the vanadium is -0.26 is the stability of this vanadium, as we see that this corresponding one for vanadium 2 plus is for the half filled cell or the half filled level in the T2G level. That afterwards, for during when we study the corresponding complex ions, we will see that the d orbitals are not of the same type, then the d orbitals can be splitted into the two level, one is the T2G and the EG. And since the T2G level has 6 orbitals, so these 6 orbitals can have the maximum electron capacity of 6, and when all the T2G level is filled, that means the 3 electrons you can have. So, all these 3 electrons is giving rise to the half filled T2G level. So, like that of our D level, D5 system has some stabilization. Similarly, for the corresponding ions in the complex species, even in the aqueous medium, when the water is serving as the ligand, so T2G level will have some stabilization. Then we can have this, all these species has some typical magnetic properties. So, all these transition metal ions, they are paramagnetic in nature. Since we are talking about unpaired electrons which are not paired, so the paramagnetism can originate from these unpaired electrons. So, for all these d electrons, we can have two types of contribution for the magnetic moment. One is the corresponding one for the orbital motion, another is the spin motion. So, the magnetic moment which is coming from the spin only moments only, that means due to the spinning motion of the electron in the system, we can use some spin only formula, that the spin only motion can give rise to the corresponding species, which whether the system is the paramagnetic or diamagnetic. That we have not encountered in case of S and P block elements, but it is the property for the D block elements where we can have the corresponding unpaired electrons in the D level. So, this is the corresponding formula, which mu is the magnetic moment. What we can theoretically also we can have some prediction, and experimentally we can also measure using some balance, the Gauss balance, which is nothing but the taking the weight of the sample in a magnetic field and in absence of the magnetic field, and from the difference we get the corresponding thing, which we can consider as the gram susceptibility value. And that gram susceptibility value can tell us by knowing the corresponding molecular weight to give you the corresponding molar susceptibility value, and ultimately that molar susceptibility value can give rise to the corresponding magnetic moment. But theoretically also by knowing the number of unpaired electron, this is the spin only formula, that is why if you know n is the number of electron which is very much similar to that of our 3D n configuration, where n is the number of electrons present in the different d levels or the different d orbitals or d cell. So, the effective magnetic moment, because this corresponding effective magnetic moment what we see is written as a corresponding subscript on mu. So, subscript on mu will give you the effective magnetic moment, can be obtained from experimentally measured molar magnetic susceptibility. What we can see using the Gauss balance, we get the chi g values, then chi g can be converted to the chi m values, and these chi m values can be expressed in terms of the Bohr magneton, and this B subscript is B for Bohr, the name of the scientist is the Bohr. So, that is the Bohr magneton value, that the Bohr magneton value can be found out. So, for any species, because these are very important parameter what we will discuss afterwards in we consider the corresponding coordination compounds, that whether these particular values can be very useful for understanding the corresponding property of all these compounds. So, this table again taken from your book, and we see that is you are very much habituated, that is why this is taken from only from your book, the CBSE book, that as we know that we can range from a D0 system to a D10 system in the ionic form. That means scandium in +3 oxidation state, because we all know that the scandium 0 has 3D1 electronic configuration. But in solution case or in the solid state, if we know that the formal oxidation state of scandium, as we have seen that the scandium trichloride. So, scandium trichloride is there. So, that scandium trichloride, what should be its magnetic property? So, since no electron is there, so it is like any S or P block element or the salt. So, it is like aluminum chloride, or it is like calcium chloride or sodium chloride. So, since it has no d electron, it can give rise to a magnetic moment of 0. So, this is there. So, by using this particular formula, what we have seen, that mu is equal to root over n into n plus 2 Bohr magneton value. So, these are all these typical Bohr magneton value, either we write as Bm as the Bohr magneton or mu b. The most latest terminology for using this is mu b, mu with a subscript b. So, using this formula, basically we get these values from a 3D0 system to a 3D10 system, because at this point again we are reaching a diamagnetic situation for zinc compounds, where we have all the levels of D are filled. So, your calculated value is 0 and experimental value is obviously would be 0. But these are the values as we put in that particular formula with the number of unpaired electrons, and as we move from 1.73 to again to 1.73, that means again when we move to copper 2 plus, we will have 1 unpaired electron. But if we see that we have more number of unpaired electron, that means we have D9 electronic configuration, but the unpaired electron, the available unpaired electron is only 1, like that of our titanium 3 plus. So, the magnetic moment in these two cases would be same, but the observed magnetic moments are deviating from the calculated values, and that deviation is due to the corresponding orbital contribution, because we can have the orbital motion, and instead of mu s values we can have mu l values due to the orbital motion of the electron in the orbitals of the compounds, and sometimes it is more diffused or more delocalized in the system for the different compounds. So, it will be in the little bit on the higher side. So, these values, if they are matching with this calculated one, we call it as a spin only values, spin only magnetic moment values, but when they are not going for these particular values, we can consider that some orbital contribution is there, and these values are little bit different for this. And we will see that the magnetic moment is basically increasing and is reaching again the manganese, like that of the different oxidation state or the manganese in the highest possible oxides, with increasing number of unpaired electrons. So, there we are reaching from 1 to 5, then again we are decreasing from 5 to 0. So, it is very simple to remember also that as we move from 0, 1, 2, 3, 4, 5. So, 0 to 5 and then again 5 to 0. So, 5 to 4, 4 to 3, 3 to 2, 2 to 1. So, if we remember this all these elements from scandium, that trivalent scandium to zinc 2 plus, we are having all these electrons from 3D0 to 3D10, and magnetic moment is changing, and we can have some idea about how the experimental magnetic moment is also deviating from the spin only value. So, these are the theoretical values for all these, and we can apply these when we also consider in our next chapter for the coordination compounds, when we will find that these values are helpful also in identifying the nature of these compounds. So, how magnetic moment can also help us in understanding or characterizing the different compounds, whether it is a solid oxide or fluoride or these are different coordination compounds. Okay. Thank you very much.